Okay, everyone, so we're looking at page 17, and just a reminder, on Friday, I am not talking or lecturing about any of this stuff. You're going to start your open note partner exam on it, okay? So make sure you're taking really good notes on this video. Okay. Because of that, I did have quite a bit that I wanted to have typed out ready to go for you. So the first thing is kinetic molecular theory, kinetic meaning like kinetic energy, and then deviation from ideal gases. So in kinetic molecular theory, we are coming up with these assumptions. Because think about gases and these molecules, so let's just say these will be my gas molecules. And gas molecules move around a container, right? Whatever the space of the container is, they're going to fill that space because they're moving quickly, they're bumping into each other, and they're bumping into the walls of the container. So these gas molecules, the first assumption that we make, and I just want to note that all of these assumptions are not true. And that's where we get to 3.6. It's when it causes deviations. So the first assumption is that the volumes of the gases are like just practically nothing compared to the volumes of the containers that they're in. And so this more or less holds true if we think about the size of these molecules within the containers. Like the molecules themselves are so much smaller than the containers that they're found in. And so if we make that assumption that the volume of the molecules are negligible compared to the container, then these ideal behaviors work out perfectly. The second one is that gas particles do not interact with each other, meaning that like these aren't going to collide and then react. They're not going to form something new through a collision. They're just going to collide. That the collision is going to be perfectly elastic. Gas molecule collisions are elastic, meaning they just bump into each other and they bounce off of each other, right? No energy is lost or gained. They just bounce and then bounce, and they bounce off the walls of the container the same way. Like whatever speed that they're going when they hit the container wall, they leave going that same speed. So we're assuming that these are perfectly elastic collisions. And then the last one, and this works really well, and I have seen so many questions on this on the AP Chem exam. So the average kinetic energy of the molecules, so if I take the average kinetic energy of all these molecules, that it's going to be proportional to the temperature. Like if I were to put my thermometer in there, it's like, what's the temperature? That's going to be directly related to the average kinetic energy. Okay, so everyone, I have seen questions where they are trying to trick you, where they're saying, and the pressure is this, and the volume is this, and I'm going to change this thing, I'm going to change the temperature, and I'm going to change the volume, but the temperature remains the same. Well, if the temperature remains the same, then the kinetic energy, the average kinetic energy remains the same. Okay, so if temp doesn't change, then average kinetic energy doesn't change. They're directly proportional, meaning if the temperature increases, the average kinetic energy increases. If the temperature decreases, then the average kinetic energy decreases. And something that's important to mention here is we kind of have a misnomer in this diagram. Do you see how the velocity vectors, these arrows, the size of the arrow represents the magnitude of the velocity, how fast they're going, and the direction of the arrow indicates the direction that molecule is going. And they all look to have velocity arrows that are the same size, and that's certainly not going to be occurring. The diagram down below does a better job. We should fix this one. So like let's say that this one has a much bigger velocity and this one's going to have a much smaller velocity. But if we consider the average then that's directly related to the temperature. So this sample is all at the same temperature. The average of the kinetic energies are directly proportional to the temperature of the sample. But that doesn't mean that every molecule has exactly the same temperature, and I can guarantee you that every molecule does not have the same the same velocity, okay, or like the same individual temperature. And we can see this in a distribution. This is a Maxwell-Boltzmann distribution, and look at the kinetic energy. So when the temperature of the sample is 1,000 degrees Kelvin, the average kinetic energy is higher than when the temperature of the sample is lower. So look at this temperature. This is a lower temperature, and we see that the average of that sample at the lower temperature is lower. Okay? So this, even though the peak is higher, the kinetic energy is lower, so that must mean that the temperature was lower. Okay? Even though the peak of this is lower, the average kinetic energy is higher, so that means that the temperature of this sample was higher. Okay? And then we can obviously see that one that was in between. Sometimes, like let's say I have a sample that's at 1,000 degrees Kelvin, there are still molecules. Think of the area underneath the curve. Like that's how we add up all the molecules. The sample size is all this area under the curve. Okay? So there are molecules that are going slower, and there are molecules that are going faster, but this is the most common. This is like our average temperature, our average velocity. Okay? And that's why when I look at this, some of the arrows are little and some of the arrows are big, but on average, they sit right here. You're going to see multiple of these graphs, by the way. And the most important thing I need you to check is the x-axis. There's two things that it could be: kinetic energy, or on different graphs, sometimes it's velocity, aka speed of the molecules or the atoms. Okay? The kinetic energy is directly proportional to the temperature of the sample. Okay? Something happens with velocity because kinetic energy is more than just velocity. The equation for kinetic energy is 1/2 mass velocity squared. So there's two components to this: mass and velocity. All right, so looking at the next page. Here's what I'm talking about. Look at this one. Oh, it's speed or velocity, and then not kinetic energy. Okay? So this graph, all of the samples, this sample, and this sample that's hard to see on this camera, are the same gas. Okay? So this is same gas. Right? And so that means that this sample, let's just pick one. It doesn't matter. Let's do hydrogen H2. So this is a sample of gas, and every single one of these was H2. So what happens if the particles start moving faster? Well, if they start moving faster, then we can see that the temperature increases, right? This is a particle speed that's lower, and then the particle speed that's a bit higher, and a particle speed that's a bit higher. Here's our average there. I'm going to draw this one because I know it's hard to see. You have your notes, though, so you'll have an easier time reading that on your notes. But here's this average, and that one's higher. So if it's the same gas, meaning that the mass is the same and the velocity is bigger, then that would mean a higher kinetic energy or a higher temperature, right? Like, think about this. H2 has a mass of roughly 2 grams per mole, or 1.008 times by 2. So 2.016 grams per mole. Okay? And so that mass is the same whether it's sample 1, sample 2, or sample 3. So I'm going to call this one sample 1, sample 2, and sample 3. So in sample 1, if I were to do half of this mass times the velocity squared, well, the velocity is the smallest for this sample, right? So I'm going to do a little velocity squared. That would equal a smaller kinetic energy, which would be a smaller temperature. It's directly proportional. Oh, we could use this symbol. Directly proportional to a smaller temperature. Now, in sample number 2, though, it's still H2 gas. So this would be half of the mass. The mass is the same, so I'm going to do the same size. So like I'm literally having the size that I'm writing the letters represent the magnitude, how big this thing is. So half of the mass. Now the velocity is bigger this time. So the velocity is a bit bigger, squared. Well, guess what? That's going to equal a bigger kinetic energy, which means that the average temperature is bigger. And we saw that, right? This was a temperature of 300 Kelvin, and this was 1,000 Kelvin. Now, our third sample, the mass is the same. So 1/2 mass is the same, but our velocity is much bigger. So we got an even bigger velocity. Squared equals an even bigger kinetic energy, which would result in an even bigger temperature, right? And that's what we see. This has a temperature, this sample has a temperature of 2,000 Kelvin. Okay? So when you look at these graphs, I need you to be checking on 2 things. The first thing, is it speed, velocity that we're talking about? Or is it speed or kinetic energy? Kinetic energy. And is this the same gas in all of the samples, or are there different gases on the same graph? Okay, I'm going to show you an example of that in just a moment. Now, the reason why the peaks are higher and then lower is because the area under the curve has to be the same for both. It's like I took the same sample. I took sample number 1 with a certain amount of moles of H2, and then I heat it up, and so the temperature is higher, and I'm not adding any more moles of this. So the area under curve number 1 has to be equal to the area underneath curve number 3. So that's where we get the flattening out. We get a greater variation in individual molecules if they're moving really fast or really slow. Okay, but on average, their speed is higher at a higher temperature, and on average, their speed is lower, right? Because zero's over here. On average, their speed is lower at a lower temperature. All right, so in the next graph, something really interesting happens. Molar mass and molecular speed at 25 degrees Celsius. So that means all samples at 25 degrees Celsius. So the oxygen, the O2 sample, and the helium sample, and this H2 sample, I'll draw it because it's hard to see on the camera. Here's our H2, and then the curve. Okay. all of these are at the same temperature. Okay, remember, if they are the same temperature, then they are the same kinetic energy. I'm not worried about this graph right now. Okay, I know that I've been told that they're all the same temperature. So that means that the kinetic energy, the average kinetic energy of O2 is equal to the average kinetic energy of helium, and that's equal to the average kinetic energy of H2. Okay. Now, I recognize that these are not all H2. O2, helium, and H2. And then I look at my axes here and I go, oh, speed or velocity. So not kinetic energy. Guess what? If we had kinetic energy graphs of these three, if it wasn't velocity, they'd all directly overlap each other because the kinetic energies are all equal to each other. Like it'd look something like this. Let's say this was kinetic energy graphs, and it'd be like, here's the kinetic energy of O2. There's my kinetic energy graph. And here's my kinetic energy graph for helium. And here's my kinetic energy graph for H2. They would all directly overlap each other. Okay. I'm going to, for just a moment right now, ignore the helium. Let's just talk about the extremes. So I just want you to look at O2 and H2. We have said that the kinetic energy of O2 is equal to the kinetic energy of H2. Okay, kinetic energy of O2 is equal to the kinetic energy of H2. Their masses are not the same. O2 has a mass of 32 grams per mole, where H2 has a mass of 2.016 grams per mole. So obviously an O2 molecule contains a lot more mass than an H2 molecule. And I'm going to represent that in the size again, meaning kinetic energy is 1/2. Okay, now this is O2. My mass of O2 is much bigger than my mass of H2. So the mass is going to be much bigger. Okay? And then same thing, 1/2, but my mass is going to be much smaller because this is the mass of O2 and this is the mass of H2. But wait, if these things have to be equal to each other, then that means the velocities are not the same. The velocity of O2 must be small and the velocity of H2 must be big. 1/2 a big mass times by a small velocity would equal 1/2 a small mass times by a big velocity. So let's see if that was true for our graph. O2, does it have a small velocity? Okay, speed. Here's our sample of O2. Oh, and look at this. The average velocity is much lower than the average velocity of the H2, which was much higher. Their temperatures are the same because their kinetic energies are the same, but due to the fact that the mass of H2 is much smaller than the mass of O2, their velocities are not equal when their kinetic energies are equal. So again, you are checking on two things. First, what is the x-axis? Is it speed or velocity, or is it kinetic energy? And then the second thing you're checking is, are these all the same gas? Are they the same sample, or are they different gases? Because if they're different gases, then they have different masses. Alrighty. So that is what we see in ideal situations. We get these beautiful graphs with these different distributions. Okay? And we need to know, what if we don't have these ideal situations? Okay? Real versus ideal. Okay? So there's two things that I need you to know. So first, just a reminder. Remember those conditions, those assumptions that we made? The first assumption was that the volume of the gas was 0 or negligible. Volume of gas particles is negligible. Ooh, how do you spell negligible? Looking it up. Okay, Negligible. Nice, thank you, Google. All right, volume of gas is negligible when compared to the container. Okay, the volume of gas is negligible when compared to the container. So then what do you think acts more ideal and which one do you think acts less ideal? What if I have this container and I put the same gas samples in both, like they're both helium gas or something like that, but one I'm going to put more of them in there. So it's like 1, 2, I'll just put 3 of them in there, okay? But in the other container, we put a lot more than that. Even though the volume of this molecule atom in this case, is so much smaller than the container, the more of them that we put in there, the more noticeable that volume becomes. And so when we have less particles, when we have something that's less dense versus something that's more dense, lower pressure versus higher pressure, then we would get more ideal, less ideal. Okay? The assumption works better here than it does here. So we're even going to write that. We're going to say more ideal. It acts closer to how it does when we make those assumptions versus less ideal. It's not going to act in the way that we expect it to under ideal conditions. Okay? Now, the next assumption that we made was that gas particles don't interact with each other, that we have perfectly elastic collisions. Okay? Gas particles do not interact with each other. Collisions are elastic. Gas particles do not interact. Collisions are elastic. Okay, now, I'm going to talk more about this in a moment, but what I'm saying right here is, what if I have two nonpolar gas particles and they're flying around the container and they bounce off of each other and they're pretty much like elastic collisions, okay? They're acting the way that we would expect in ideal behaviors. But what if we have two molecules that are polar? Okay, this is water. Let's make it water vapor. So it's flying around the container. Oh, did you see that? It bumped into it. Oh, but then it grabbed onto it. This is not an elastic collision. Okay? So the stronger the attractions between molecules, the further away it moves from ideal. So if I have a gas that's nonpolar, like this is a model for C2H6, and this is nonpolar molecule, versus H2O, which is polar. Okay. This is more ideal. It would act in a way that we would expect, and this is less ideal. it acts in a way that we don't expect under ideal gas law conditions. Okay, and then the last one we're okay with. Okay, nice. So there are two ways that we can deviate from ideal behavior, okay? And then students get these mixed up, so be careful. The first is the environment. Like, I could change the environment to make gases act more or less like an ideal gas. But there are also specific gases that act more or less like an ideal gas. So let's draw a line. Let's talk about the environment first. Okay. So, imagine I have two samples, but they are the same gas. So I'm not comparing gases. I'm not saying which gas is acts more like an ideal gas and which one acts less like an ideal gas. I'm saying if I have two samples of the same gas, what could I do? What could I change that would make that gas act more like an ideal gas or less like an ideal gas? Okay. I watched a video one time when I was studying this, probably my first year teaching AP Chem, yeah. And this is how the lady remembered, and I never forgot. So, ideally, we have hot lips. Okay, I know, that's so silly. But this is where what we're saying. A gas will act more like an ideal gas at high temperatures and low pressures. Hot lips. High temperatures, low pressures. So if I take a gas sample and I increase the temperature to a higher temperature, let's do higher temperature. Okay, so the higher temperatures make it act more like an ideal gas. If I take a sample and I lower the pressure, then that's going to make it act more like an ideal gas. Okay. Alrighty. So an example of this might be like, what if I have 3 containers with the same gas inside them, and the temperature of the first container is 50 Kelvin, the temperature of the second container is 100 Kelvin, and then the temperature of the third container is 150 Kelvin. And then the pressures. The pressure in the first container is 1 atmosphere. The pressure in the second container is 1.5 atmospheres. Oh, I'm doing it backwards. Let's make the first one 2. 2 atmospheres. The second one's going to be 1.5 atmospheres. And then the third one, the pressure is going to be 1 atmosphere. Okay. Which container that's the same gas floating around in there, H2 gas, whatever, which container does this gas act more like an ideal gas? That would be the high temperatures, low pressures. Okay, now, if the temperatures and the pressures are the same, there are certain gases that will act more like an ideal gas when compared to others. Okay, so now I'm not talking about the environment. I'm talking about the type of gas molecule. Okay, so I'm gonna write like a continuum where the lowest down here, this is gonna be most, actually, least ideal to most ideal. Okay, least ideal to most ideal. Boop. Okay. So, we know that we don't really want attractions between molecules. Like, if we get these attractions, then we can't get these beautiful elastic collisions, okay? So, first thing, nonpolar molecules are better, they are more likely to act like an ideal gas than polar molecules. So, least ideal is when a molecule is polar. Polar molecule. Okay. Now, nonpolar molecules, it depends on their size. The larger the molecule is, the further away it moves from ideal. So the small nonpolar molecules, and I'm talking both size and mass, both. The small nonpolar molecules act the most like an ideal gas. The larger nonpolar molecules are better than the polar molecules as far as acting like an ideal gas, but they are not as good as the small nonpolar molecules. So an example would be a small nonpolar molecule, H2. That's a great one. A large nonpolar molecule, what about C2H6? Okay, and then even though this polar molecule is smaller, H2O, than the C2H6, it is the furthest from ideal when comparing those three. Okay, this acts like the most like an ideal gas, and this where we get perfectly elastic collisions, they just bounce off of each other, and this one acts the least like an ideal gas, because when they go to collide, they kind of try to stick together. Okay. Alrighty, I'm just a couple minutes over time. I apologize about that, but that wraps up this conversation. We'll get your test started on Friday. We will finish it up on Tuesday, and then we will grade it on Tuesday. If you guys have any questions, please, please, please do not hesitate to email me. Okay, thank you all.